Let me tell you a brief story about hydrogen. I'm from a small village in the northern part of Germany, close to the port town of Bremerhaven. There's a small train line running from Bremerhaven to the larger city of Hamburg, about 100 kilometers to the east. The train passes by my home village and continues its way through green pastures and meadows, stopping by several small villages and smaller towns with a dozen of cows looking on. It's very idyllic and very rural. And when I say it's a small train line, it really is small. The train only has 2 carriages, and for some stops, you actually have to tell the driver in advance that you need to get off, otherwise the train won't stop. Needless to say, this is not an electrified train line. And until recently, the train has been running diesel engines. But for a couple of years now, the train line has included 2 hydrogen-powered trains. And now whenever I visit my home village, I'm very impressed and I marvel at this quiet and very futuristic train whose exhaust is pretty much only water, maybe a glimpse into our hydrogen future. Welcome to the Coffee Talk. Today, we will take a look at our hydrogen future. Over the next 60 minutes, we will examine why hydrogen plays a central role for our future societies, where we are in terms of producing and transporting hydrogen cheaply and efficiently, what kind of global supply system is emerging, and what kind of roles Germany and Japan play in all this, and why collaboration between these 2 countries is important. To shed light on these questions, we are very fortunate to have with us today 2 experts in hydrogen research, Professor Dr. Christian Sattler of the Institute for Future Fuels at the German Aerospace Center, DLR, and professor at the Technical University Dresden, and Professor Dr. Tatsuya Kodama from the engineering department at Niigata University. Thank you very much for being with us today. A quick note to our viewers, you've probably watched the Coffee Talk already. As you know, there's a link posted to the DWIH website, to the website Slido. You can use this link to post your questions. If you want to get in touch with our guests, please also check the website. There are the links that you can use to get in touch with them. Some of you already prepped us with some questions in advance. Thanks very much. We'll get back to these questions in the course of our talk today. Also, one quick note. It seems like we picked the perfect time and day for our talk. I was unaware of it when preparing the date. But only 1 hour after our talk, the Hydrogen Energy Ministerial meeting will take place today, with speeches, among others, by the German Federal Minister for Economic Affairs and Energy, Peter Altmaier, and the Minister of Economy, Trade and Industry in Japan, Hiroshi Kajima. So we really picked the perfect time and date. Christian, I wanted to start with something pointy, and I was thinking about the following question. Is hydrogen really the energy source of the future? Is this what we've been waiting for all along?
Yeah, good morning, Axel. Good afternoon to Japan. Hydrogen is a very special molecule. It is a very good energy storage, chemical energy storage. Therefore, it can play an important role in our future energy system, but it's a chemical molecule, so it's very important in chemistry. It's around in chemical industry for over 100 years, and therefore we have to look at it in a much wider context than only as an energy vector. It is absolutely crucial, for example, for the production of fertilizers. There are 2 large production areas where hydrogen is used today. This is for the upgrading of crude oil and for fertilizer production. And especially as our population is growing, we will need even more fertilizer in the future. And hydrogen is absolutely vital to that. And today, hydrogen is produced mainly from fossil resources, mainly from natural gas, a little bit from coal. And we have to shift this to renewable energy to avoid the CO2 emissions. So by putting hydrogen in a wider context in our energy economy, it will be an energy vector for replacing some kind of other chemical fuels, but it also will remain a chemical that we need just for our living. And we have to transport it and produce it in large quantities in areas where we probably not produce it today, but which will help us to establish such a global grid of hydrogen production. So in short, yes, it will play an important role in our energy system, but there are other applications where we desperately need hydrogen as well.
This is actually very interesting, because I think most people are probably like me. When we think about hydrogen, we first think about hydrogen-powered cars, trains, whatever. But what you're saying is that there's actually a very large part in the economy where hydrogen is needed, and that doesn't relate to energy.
That's true. And it will remain like this, because otherwise we will not produce enough food, or there are other important processes, especially in heavy industry, where we need hydrogen as a reducing agent. So for example, in developing our steel production, for example, we could use hydrogen. And there are other large production processes where we can use the hydrogen instead of carbon that we use today. But as well, we can use it as an energy vector. And you mentioned the different transporting systems. It starts actually with ships that could be operated with hydrogen. Large vessels can use the hydrogen as a fuel, but it also could be used for trains. You mentioned that the train in northern Germany, we know that these trains are very much looked after. The different companies try to replace diesel engines with hydrogen fuel cells, and therefore minimize the emissions of their non-electrified train systems. We also will use it for road transportation, specifically for trucks that have to run for long distances, so that they should not wear too much load from batteries that bring them to the necessary distance a day. The hydrogen system will provide larger ranges with lower weight, but also maybe for passenger cars. There are some on the roads. I like to drive them. They drive nicely. I would like to see even more of them on the road. And then, of course, also.
Sorry to interrupt you, Christian. So are you already driving a hydrogen-powered car?
Yes, we use one. We have two sites in my institute in Germany, and it's about 75 kilometers apart. So to move between the two sites, we have a hydrogen car that works perfectly. We use it now for nearly 3 years. There was not a single failure in that 3 years. It's brilliant. And all the people are very happy to drive it. It's smooth, it's quiet, it drives nicely. So I really like this.
Yeah. And where can you fill it up? Do you have to fill it up at your institute?
No, we have a quite well-established hydrogen refueling system in Germany. So second best after Japan. Japan is leading here in the world. But even in Germany, we have about 100 refueling stations, and therefore it's no problem to refuel the car. On my way from Cologne to Jülich, there are 3 refueling stations, so it's no problem.
Excellent. Tatsuya, if I may ask you, are you driving a hydrogen-powered car, or is there something in your daily life where you can use hydrogen already?
Yeah, I'm living in the Niigata city. So, but in the Niigata city, we have only one hydrogen station. So, no, Kuchan said Japanese is a leader to have a hydrogen station, but almost of all located in the Pacific Ocean side, like Tokyo, Osaka, Nagoya. I live in Japanese seaside. My city has only one hydrogen station, so it is difficult to refuel the hydrogen.
Yeah.
So that is a problem, I think, the only hydrogen car currently. So.
But I would think we're probably still at the very beginning, right? So this is probably something that would be expanded in the near future. Correct me if I'm wrong, but to me it seems and I don't want to sound biased, and I don't want to advertise hydrogen on purpose because that's the topic of our talk. But it seems to me it might be much easier to establish a network of hydrogen fuel stations rather than expanding a network of electricity plugs so that you can fill up your electric car. Or how would you see the future? Is it side by side? Will we have hydrogen powered cars for some applications, electric cars for others?
If you have the shall I? If you have the chance to plug in your car at your home, an electric car is very versatile. It's very easy to use. If you don't want to run too long distances, so that the batteries don't have to be too big, too heavy, too expensive, then it's a very nice way to drive, and it will probably be a good choice for probably more than 90% of your drives anyway. If you have special use of cars, so especially long distances, then hydrogen might have an advantage. And if you live in places where it is difficult to plug in your car every day, so in areas where you don't have the chance to have your own plug-in system, then it also is useful to have a central station where you can refuel the car fast and easily, and therefore there will be choices, but for many applications battery electric cars are absolutely excellent because they're so easy to use.
So for long distance, yes, Tatsuya?
I think for the people driving the light car, very small car and compact car, maybe electric car is the best choice. But for example, in a truck, bus, and heavy car, I think they need more power. So in this case, the hydrogen, they have to use the hydrogen. So also problem is the cost of the car. So FC, hydrogen fuel cell vehicle, is still expensive for the people. And also now, if we put also battery plus FC fuel cell, it makes the car more expensive. So Toyota is now developing the hydrogen engine car. So hydrogen engine is very simple and must be much cheaper than a fuel cell car with batteries. So hydrogen car will be the one of the choice. So
what would be the difference to the hydrogen powered car? I think Toyota already has a car. I looked it actually up in ahead of time. I think it's about 65,000 euro. So it's not sort of the average price range, I would say. What would be the difference for the car you just mentioned?
There are many varieties. So if you have hydrogen, so one of the to get the power for the fuel is one of the option is engine. So engine doesn't use any fuel cell and battery. So just engine, like gasoline car has an engine, but just replacing the fuel from gasoline to the hydrogen. But we have to use another engine especially for the hydrogen. But fuel cell is kind of the very high technology equipment. So it's a little bit expensive than this kind of the regular engine. So also battery is very expensive. So most expensive car has a FC plus battery. So next one is probably FC. Next one is the battery, and bottom one is cheapest one is maybe engine car.
I see.
hydrogen
Okay, so
engine.
FC then fuel cells, right? Yes. Okay.
FC is fuel cell,
Yeah. In the future, Christian, you mentioned ships. Will we see other applications? Will we see hydrogen-powered airplanes?
Probably yes. That's actually a technology that was already developed in the 1980s. There were the first flights with hydrogen as a fuel in aircraft. It will be a very nice fuel for short and medium range aircrafts. It will be very clean. If you produce this from renewable energy, you only put water in the atmosphere. So I think it's a very good idea. It might be difficult for extra long range aircrafts because then the volume of the hydrogen that you have to transport will be very large. So the amount of space for other freight or passengers will be reduced. Therefore, it's probably not the right fuel for long range flights, but for short to medium range, it's definitely a way for clean air transportation, and therefore it's exactly what we need.
Yeah, well, a couple of questions ahead of time, like I said, and one very good question, I think, probably reflects a general concern about the safety of hydrogen. It seems very powerful. Also seems that if you crash your car, you really might cause problems. What's the state there? Or is it fair? Is it sort of on par with gasoline-powered cars?
As a chemist, I would look very critically on all the energy systems that are used to power something. There is always the possibility, no matter if it's a solid state battery or it's a liquid like our petrol, or if it's a gas like hydrogen, there's always the energy in this material. And then you have to see how these materials behave. If you have hydrogen as a gas that is extremely light, if anything happens, the gas is blown away so fast that not much will happen. It's not that this thing explodes. It's just as that you will get a flame that burns very shortly and then it's gone. You know it from the liquid fuels, how the liquid fuels burn when you ignite it. It stays on the ground, and that's the dangerous thing. And therefore, the gas is more safe than the liquid fuel. Additionally, there are substances in the liquid fuels that are toxic. Hydrogen is not toxic, but benzene is. And then when you look at the batteries, there are light metals in it, specifically lithium, and lithium burns, and therefore you have a solid that burns, and it's very, very difficult to put out the fire if it burns. So it's an issue with all the energy-rich materials, and there are specific dangers, but if they are not reactive, if they don't provide the energy, you can't use them. Then they might be safe if you put a rock in your car, but you can't get the energy out of it. So we have to deal with this danger if we want to use power coming out of whatever system.
Yeah. Thanks so much. I remember there was another question actually to that extent. I think along the lines, if you have hydrogen, I mean, to me, well, first of all, the exhaust seems to cause no problems, while we basically have water with some minor side products, I think. But if we have hydrogen available and it gets dissolved in water, for example, I don't know if that's actually possible, but since we had the question, it was a question about safety. If we dissolve hydrogen in water, is that a problem? Is it toxic? Does it cause any problems? Does it just evaporate into the air, or what would happen?
Yeah, some people say the hydrogen dissolved water is very healthy for our body. So yes. So I think the hydrogen in the water, if hydrogen dissolved in the water, I don't fear it's dangerous.
So you could actually stop your car and get a health trainer. I'm just joking.
Well, for example, you know, hydrogen has very, very diffusible. Diffusibility is very high. So if you find a leak from hydrogen cylinder, But if you got the right, for example, 5 meters distance, but nothing happened. So hydrogen can quickly diffuse. So the ignition limit is 4% in air.
Mm.
So it can't be reached to the 4% in the air. If 5 meters, there is a 5 meters. If you if you make this right to cross to the just leaking point, it must explode, but like that. So comparing the other fuel like gasoline or kerosene, I think if we use the outside, hydrogen is not so dangerous, rather safe. But we have to be careful in a room. For example, sealed room, sealed space, hydrogen go up to the the ceiling and collect and the concentration become high. In this case, that is very, very dangerous. So
if you have confined spaces, a bit like the inside of a building.
Yes. You remember in the case of the nuclear power plant accident, there is a big explosion. So it is the hydrogen is collected on the building, so explode. So if it's open space, it's never happened.
Yeah. Thanks for mentioning. I remember hydrogen built up inside the building, and it basically blew the building, the outside apart. That's very interesting. To me, I've always liked hydrogen. I think it seems so clean. So I mean, comparatively, easy to use, or maybe also safe to use. And I remember when I was in, I think, 7th or 8th grade, there was in the late 1980s, we already talked about the potential of hydrogen energy in my chemistry class. And that's more than 30 years ago now. What took us so long to get where we are? Or maybe to phrase it in a different way, were there major technological advances over the past 30 years that have helped developed hydrogen to where we are now, Christian?
There were more societal advantages over the last decades. I mean, what you mentioned, the development in the 1980s came from the oil crisis in the 1970s, when our former colleagues looked for solutions how to overcome the dependency of oil. And one of the ideas was to use nuclear power plants to produce hydrogen as a fuel that could be used then in, for example, in transportation. And when the oil price went down and there was sufficient oil available on the market in the 1980s, there was no necessity to develop the hydrogen technology further. So there was big development in the 1980s, and it was discussed very openly how to get into a hydrogen economy. But then it went down because there was no need to do. And then when the Kyoto Protocol was signed in 1997, then the discussion started again. How will we get to a clean environment? How will we stop climate change? What kind of energy vector is the right one to do that? So then the discussion started again. And so in the beginning of the 2000s, hydrogen was back in the mind of the people. And since then, the development went on quite slowly over the time. There was a peak in about 2005, then it went down a little bit, and then it went up again. And now, since the Paris Agreement in 2015, we see a very strong development into the direction of reducing our climate emissions, mainly CO2, but others as well, so that we can achieve the goal of less than 2 degrees temperature raise until the end of the century. So since then, hydrogen has become so interesting for many applications, especially, and that's important, if it's produced not from fossil resources, but from renewable resources, or in some areas where you have nuclear power, from nuclear as well.
So it's also really about the political environment. Now, both Japan and Germany, we want to become zero emission economies. Now, the issue probably has gained more urgency than.
it's not only political, it's societal. So, I mean, it's not only the politicians that say we want to live in a clean world, we want to live in a world where we don't have to fight with the climate, but therefore the society is behind it, and the politicians have to find the ways how to organize that. And therefore, it's a joint venture, thankfully. And therefore there is a big acceptance for this development.
Tatsuya, we just had a very good question from the audience, which I think fits nicely. The question is, what's taking so much time about the realization of hydrogen-driven vehicles? Is it a matter of efficiency, of technology for fuel cells, for example? Is it the infrastructure, the surrounding infrastructure? Is it safety issues? What is the main obstacle currently?
Main problem is cost of hydrogen production using the renewable energy sources. So yeah, of course there are many problems. For example, hydrogen station, hydrogen pipeline. There is no hydrogen pipeline. How to transport, how to store the hydrogen also a problem. So hydrogen is a gas. So if we store the gas in the containers, cylinder, it becomes very huge. So it's very expensive one. So storage, transportation, usage. But the main problem is the cost, I think. If the hydrogen from the renewable energy can compete with other fossil fuel, like especially natural gas. In this case, the probably hydrogen can distribute very quickly in Japan, Germany also. So now our government are trying to establish how to store, how to transport the hydrogen, especially for the foreign country. But we need to think about but the essential point is actually cost of the hydrogen, I think. So
let's talk about costs then. That's very interesting. Actually, maybe before we start dealing with producing, with the cost of production and distribution, I think it popped up briefly at the beginning how hydrogen is produced, and I recall that there are all these colors, right? There's brown hydrogen, there's gray hydrogen, blue hydrogen, green hydrogen. Now, what's the difference, and what kind of hydrogen do we want?
Okay, so there is 4 hydrogens kind. It's like one of them is brown hydrogen, gray hydrogen, blue hydrogen, and green hydrogen. So brown hydrogen is the hydrogen produced using the coal, coal.
Okay.
So it is a kind of the very cheapest hydrogen, but emitting the most amount of the CO2 if you use. So normally we use the coal gasification to produce hydrogen, but it emits most amount of the CO2 when we produce hydrogen. Next one is gray hydrogen. Gray hydrogen is produced from natural gas. So comparing the other fossil fuel, coal and oil, natural gas is more green. Green is the producing less hydrogen, but still emit hydrogen. No, CO2. Sorry.
Less CO2 then. Yes. Okay.
But next one is blue hydrogen. Blue hydrogen means we use the coal, natural gas oil to produce hydrogen, but we capture the CO2. Then we store the CO2 in, for example, underground. That is we call it CCS, carbon capture and sequestration. So if we combine the normal hydrogen production technology like coal gasification and natural gas reforming with CCS, in this case we don't emit CO2 because we catch and store it. So in this case we call blue hydrogen.
We still use fossil fuels to produce it, but we capture the carbohydrate.
Yes. And last is green. Green hydrogen is ideal. So using the renewable energy, we produce the hydrogen. So in this case, the hydrogen is 100% CO2 free. So that is for hydrogen.
Yeah. What's production? So we basically want to get to green. What's production currently like in Japan, for example, or in Germany? Where's the main focus? What's the main source currently?
Yeah, we need a renewable energy source. That is, one is hydropower, and wind power, and also solar electricity using the solar cell. And in my field, we use the solar high temperature heat. So
solar high temperature heat.
Okay.
You have to explain that. Yeah, I think when I think about hydrogen production, I think about electrolysis.
Yes.
Right.
In the case of you use the hydropower or wind power or solar electricity, using solar cell. In this case, you need electrolyzer to split water. So, but another way is solar thermochemical process. So in this case, we don't need electricity. We produce the hydrogen from heat. So it is a different way completely. So you need to think about first which one, electricity or heat.
Yeah.
So actually, there is a hybrid process, combine the heat and electricity. So complicated a little bit.
We get to the following. So we have sort of electrolysis. That's what I know from chemistry class in school, right? You use electricity to split water into hydrogen and oxygen. You can use the hydrogen, but you're saying there's also now a different process, and this is actually why it's great to have you two here today, because I think this is also the main focus of both your research, right? You use thermal production, if I may call it that way, to produce hydrogen. What's the Christian, if I may ask you, what's the advantage compared to electrolysis of this process?
Well, let me get back to the history. When our colleagues worked on these processes in the 1970s, they thought about what is the most efficient way to bring the power from a nuclear power station into a fuel like hydrogen. And they developed these processes because of the high efficiencies. So if the energy form is electricity, you can use the electrolyzer. If the energy form is heat, you can operate these chemical processes, thermal processes, to produce the hydrogen. And the case is that the potential efficiency of these processes are extremely high. And the coupling to a heat source is rather easy if you go for renewable power, because heat can be stored much better than electricity. It's much cheaper to store heat than to store electricity. So if you run a solar plant over a year, it's definitely more efficient to store the heat, operate the hydrogen production thermally, instead of store the electrons and operate the electrolyzer.
So for storing electricity, you would need batteries, but
exactly.
how would you store heat?
Well, there are different methods. It depends very much on the process that you want to operate. You can store it, for example, in bricks or in sand or in such materials. It is a little bit like in the big blast furnaces in iron and steel production, where you use waste heat from each process to heat the next process. There are big such high temperature storage systems. About the same technology could be used for the hydrogen production. But there are other processes that work at lower temperature, and there you could use, for example, molten salt as a liquid, or phase change materials to give the energy free, or even thermochemical storage systems where you store the energy in in a chemical bond, and then you release it when you need it for the hydrogen production. So there are a number of different storage systems that could be applied for the technologies. And there is another big advantage. We talked about these industrial processes already, and many of them need a lot of heat. So if you have the heat available anyway, you can integrate it. And as you need the hydrogen very often in this industrial plants, there's a very nice combination that you produce the hydrogen on site or close to the use of the hydrogen. And you can even scale this up so that you can provide the hydrogen, can provide the heat for the industrial process, and store the hydrogen for the use as an energy vector. So there are a number of arguments for the high temperature processes. However, it depends on the site where you are located. So we will not set up a large solar thermal plant somewhere in Japan or somewhere in Germany, but we will go to the solar belts or solar regions of the world. This is in the large deserts, or mainly in the large deserts of the world, where it makes sense to use such high temperature application.
That would have been my next question. With electricity, okay, so you need a source of electricity, a source of heat. You would probably need a lot of sunshine. Yeah. What for Japan, for Germany? What areas are important then? Tatsuya, where's the focus from Japan? Actually, I always thought Japan gets a decent amount of sunshine, but that's not enough for.
Yep. Many people already knows. Maybe you may know. So Japanese target of the hydrogen utilization is very huge. For example, the government target is by 2030. Japanese government is aiming the 23 megaton of the hydrogen from the foreign country.
23 megaton, okay.
Yes, yeah. Yes. Also by 2050, 20 megaton of from the foreign country. So that's so Japanese government have to develop how to transfer the hydrogen from foreign country to Japan. So hydrogen supply chain is now the Japan have to develop, and also the cost reduction of the hydrogen in using especially I think the solar energy. So using the solar cell or solar heat to produce hydrogen less than at least 10 Japanese yen per kilogram, 10 yen, Japanese yen per normal cubic liter of the hydrogen. So
yeah.
So also Japanese aiming to this hydrogen should be used in power generation. So hydrogen have to combust in the turbine to produce hydrogen. So that is we need to use the hydrogen with mixing combustion with methane, or using the existing gas turbine. Otherwise, we have to do the hydrogen combustion by mono combustion turbine.
Okay.
So about the hydrogen, we are developing we have to develop this kind of technology. Also, already Japanese company, Kawasaki Heavy Industry developed the hydrogen turbine. So I think it's already it can be commercialized. Can be commercialized, I think.
So we would basically end up with some sort of global hydrogen supply system you would produce in sunny regions for Japan. I remember from our preliminary talk, you mentioned Australia plays an important role. It's comparative proximity to Japan. It also has lots of sunshine. It's very hot, in fact. Question for Germany: what kind of areas are, or what partner regions play an important role for Germany?
For Germany, it's obvious that the closest sunny areas are in Southern Europe, so Spain, Greece, southern Italy, but then Northern Africa is very close as well. So this is the closest regions to produce hydrogen, and there is already as well a power grid as a pipeline grid established that could be used to transport either electricity or hydrogen from that region into Europe.
Yeah. So we already have hydrogen pipelines, actually?
No, we have natural gas pipelines, but we could use them easily for hydrogen as well. You can either mix the natural gas with hydrogen or use it purely for hydrogen. For example, in the Netherlands, they just change a lot of their natural gas pipeline grid into a hydrogen pipeline grid, which is not so difficult. And then they could use this as the backbone for hydrogen production. Has to do something with the large harbors on the coast like Rotterdam, but also in Belgium like Antwerp. And this is these are the gates for Europe to import hydrogen. So it's not limited to the connection to Northern Africa or Southern Europe, but it will be actually a global market for the energy vector. And like we get our oil presently from the Middle East, or we get coal from South Africa. We could import hydrogen from South Africa, or even hydrogen from Australia or from South America. And it's not only, well, we do the high temperature development, but there is a lot of areas where you have sufficient wind power, where you have hydropower. So countries like Canada, like Norway, like Chile, they all can produce the energy vector. This will have an influence on the worldwide market because there are more producers than we have for large amount of fossil resources presently, probably. So this is a development that will take place, and then there's a market on how to get the energy vector to your country where you need it.
So we might also have other countries that, like you just said, that might rely on electrolysis, on electricity, basically to produce hydrogen.
Absolutely.
Then we have sort of like a new global supply-demand system that might be slightly different, of course, from the oil, the fossil fuel-based one, but that might function very, very similarly. That's very interesting. Tatsuya, yes?
Yes. Related to the hydrogen technology, actually ammonia is now important material because the we need to convert the hydrogen to the hydrogen carrier. So ammonia is one of the very promising hydrogen carrier recently. So related to the ammonia utilization, now the many technologies developed for the hydrogen mixed combustion with coal, with natural gas. So I think it is very important thing because in Japan we have many coal-fired power plant, but without any effort to reduce the hydrogen emission from the coal. We cannot, Japanese industry cannot, install the new coal-fired plant. In this case, we need to combine with ammonia, and we have to reduce the CO2 emission. So I think it is very important to use the existing power plant. Because if we put the newly power plant, for example, for the of course, as I said, the hydrogen turbine technology has been developed, but we have to install the newly, so it's very costly. So if we use the ammonia from hydrogen, if we use this ammonia to the existing power plant, like a coal-fired plant, it is very effective about the cost.
Okay, Christian mentioned for continental Europe, there might be some sort of pipeline system, or maybe also existing pipelines that you could use. Now, Japan being an island nation is a bit more difficult, but how would you transport hydrogen to Japan? You mentioned ammonia, so you convert it into a different substance that would be easier to ship. Are there other options?
Yes, there are other options. You can use it as liquefied hydrogen. This is the technology that is now or shall be demonstrated between Japan and Australia to ship the liquefied hydrogen. I think it's a joint venture between Kawasaki Heavy Industry and Shell. Then you can bind it in so-called liquid carbon hydrogen carriers, liquid organic hydrogen carriers, so LOHC, liquid organic hydrogen carriers. These are organic molecules that easily can take up hydrogen and release hydrogen. So like methyl cyclohexane, don't be scared by the name. It can take up 3 molecules of hydrogen. Then you can ship it from where the hydrogen is produced to where the hydrogen is needed, for example, to Japan, and then you release the hydrogen, and then toluene is produced from it, and toluene can be shipped back to the place where you want to get the hydrogen. So it's you get a high energy storage density with such materials as well, and there are many more of these materials that could be used to store the hydrogen. Then you don't need the low temperatures or the high pressure to transport the hydrogen. So these are possibilities. And yes, Japan is an island. Therefore, transport by tankers is definitely the way to go. And Japanese is also a country where you have a lot of earthquakes. So it might be, from an outside point of view, easier to transport it on the sea than to transport it by pipeline. You have a lot of mountains in the country, so it's not so easy to do this, but you have a lot of coastline and a lot of harbors, so it's quite easy to ship it to anywhere you want.
Yeah, I would imagine so. And Tatsuya mentioned it's fairly cost efficient. Where are we now? Are there, I mean, it all boils down to how expensive hydrogen would be compared to other resources. Where are we now? Is there a lot of room for improved efficiency? What kind of mode of transportation, for example, do you
about the cost? You mean mainly?
Yeah, the cost of production, but also the cost of transportation. Because I suppose it really only makes sense, right? If we get a lot of energy out of the whole system without investing too much.
So may I use my slide?
Oh yes, please.
Yes, sure. Yes. So, let me share.
Because I remember that might reflect the debate over solar panels maybe 20 years ago or so. At that time was still fairly expensive, but the price really has come down a lot, maybe more than people would expect.
About the hydrogen costs in Japan, now the currently hydrogen is 100 Japanese yen per normal cubic of hydrogen.
So it's about €1 roughly, right? Slightly less than €1.
This is very expensive. If you use this hydrogen for the power generation, so the power generation cost is 52 Japanese yen per kilowatt hours. So normally now less than the price of, for example, if you use the coal and natural gas, I think current cost of the power generation is less than I think 10, like 5 or something like that, using the fossil fuel or nuclear power. And but this is so 52 is very expensive.
Yeah, so it's 5-6 times then.
Yeah, okay. So we did in the case of Australia, we did 2016. We estimate the hydrogen cost, comparing the PV electrolysis and solar some chemical process. This is our technology. This is electrolysis using PV. at the time, the PV cell is very expensive. That is 4 years ago, and in Australia, CSIRO, that is the national laboratory in Australia, they estimate probably they produce the hydrogen 11 per kilogram of hydrogen in Australia. At the time, we estimate the cost 4 to 6 kilogram of hydrogen if we use our process, solar thermal chemical water splitting. Yeah. But now, PV is quickly priced down. So recently, they start to say probably in 2030, the 2 kilogram of hydrogen is possible.
Yeah.
So also in our case, actually, cost share, I think over the 50% of the cost share is due to the solar field cost. So 4 years ago, we used this value, but now this is new solar field cost for the 2030. If we use this value, it's this price also go to the around the 2 or something. So cost is now competing.
Yeah. So it's yeah. I'm a little bit puzzled because, but I think the numbers above they're per liter and below they're per kilogram. Are they comparable? Because I'm looking at final fuel, right, and it shows very low cost for the above 4, but this is comparable, right?
Yep. Yes. This is another process. So in this case, in the case for the producing I think in the case of this one is maybe methanol or something. This is different because in this process use the brown coal, natural gas, biomass. So in this case, we produce the hydrogen and carbon monoxide. That is syngas. Syngas can be converted to the liquid fuel. So this is different. So in this, if you compare this solar methanol with the hydrogen, maybe you can see this line. This is the price per gigajoule.
Okay. So, I see. Okay. Yeah. That's
anyway, Japanese target of the hydrogen is. If we talk about the Japanese yen per normal cubic meters, that is 30 yen, 30 yen by 2030 and 20 yen by 2050.
Okay. So that's like 15 cents, something like that. Yeah. Okay.
But now 100. So
by 2050, yeah. But thanks for the slides, Tatsuya. Thanks very much. Quick question to the two of you: how many years before hydrogen is cost competitive until it can be a good competitor to other resources?
That brings us back to the introduction. It is today. Yeah, I mean, we have to change the production over time, and it will be a continuous process from shifting from using natural gas to produce the hydrogen into green hydrogen, and the market will not accept large changes in the price. So the technologies will improve, and the larger the production capacities are, the lower the cost will be, as Tatsuya just explained. And therefore, there will be a continuous development on the market for hydrogen, and it will not change much in the price over the next decades. Well, okay, thanks. The normal inflation, of course, so the price will rise. That's true for sure. But
because of course we all know these graphs, right? Adopting new technologies, especially vis-a-vis competing technologies, it has this extended line at the beginning where it takes time and sufficient customers, users adopt the new technology, and then eventually it picks up. We're slowly approaching the end of our talk, but now let me just ask you about Germany and Japan, because from what I see, I think both Germany and Japan are actually pretty much at the front line of hydrogen technology, technology development. The two of you, you've been working together for quite some time, I think already. How long
More than
have you known
15 years, yes.
15 years, okay.
More than 15 years.
How did this cooperation develop?
Well, we met at conferences where we work in the same area on using solar energy for hydrogen production. So this is how Tatsuya and I met a long time ago. And since then, we work together and try to even strengthen this over time. It's not so easy between Germany and Japan, but this doesn't scare us. We will continue that, and we further strengthen that. And we believe there is a big benefit for all of us. And you mentioned the meeting of the ministers later today. So you see that there is a will between the two countries to closely work together on hydrogen. Hydrogen has a very high priority in German policy, industry and economy, and the same like in Japan. And so we believe it's a natural way how to develop that. And there are joint ventures going on, like in car making between Toyota and BMW. Toyota developing fuel cell systems, for example. BMW making lightweight structures which can be combined in joint ventures in car manufacturing. Tatsuya just mentioned the internal combustion engines working on hydrogen. This is something that actually we developed at DLR in the 1970s. So the first car was a BMW with an internal combustion engine in the 1970s. And then BMW had some demonstration engines in the 2000s, and I think it's a good idea to look deeper into the internal combustion engines again, because they work. And if you don't produce any harmful off gases, then it's a nice and cheap way to use the hydrogen. However, there are a lot of things to develop, and I believe especially for us as researchers, working together is extremely important and will help us all to be faster, to be more efficient, to find the right answers, how to improve all these basic science up to the development into application.
So it's about sharing know-how, ideas. It makes a lot of sense, I think, from my perspective, because both Japan and Germany are already very advanced. So there's a huge foundation that both can build on. And obviously sharing ideas, sharing knowledge would probably speed up the process of developing technologies further. Tatsuya, what kind of obstacles do you see, or maybe even a better question, where's a lot of potential for working together for Germany and Japan currently?
Yep. So if I say about our field, solar, some chemistry, some chemical production with hydrogen, actually, DLR is the senior than Japanese researcher. So Japanese industry, Japanese industry and the researcher have to learn from the DLR researchers, because DLR did many demonstration with using the solar facility with South Spain. So DLR is a top leader of this technology. So Japanese industry had a very nice, excellent technology like the turbine and high temperature storage. But Japanese industry doesn't know how to operate how to get the high temperature from sunshine. So Japanese industry and the researcher have to collaborate with the institute like DLR, who has a very a lot of the experience on this field.
Thanks so much. So it's also sharing competitive advantage, right? Both Germany, Japan. Niigata University, the DLR in Germany, you both have a lot of strength in certain areas, and it makes a lot of sense to pool them. Obviously, if researchers are interested in the topic, they're very welcome to contact you, I would assume. Thanks very much to the both of you, Christian and Tatsuya, for this very interesting talk. I certainly learned a lot today, also about the future potential and actually about different ways to produce hydrogen that I wasn't aware of. It was very interesting. Thanks so much for making time for our talk today. Thanks also for everybody who was watching, who made time for the coffee talk. As I mentioned at the onset, if you want to get in touch with Christian or with Tatsuya, please take a look at the DWIH Tokyo website. You can find all the information there. Please also do check the website and the DWIH's social media channels for news and events on research and innovation in general from Germany and Japan, and also subscribe to the newsletter, which I think is always a very good source of information and also of upcoming events. Today was an exception. We usually try to meet on the first Tuesday every month. Today was a Monday, but as it turned out, we picked the right day. We had 2 hours head start before the ministers' meeting. Thanks so much, everybody, for joining. Thanks for the illuminating talk, Christian and Tatsuya, and see you next time then.
Thank you for inviting us.
Thank you for
See you.
inviting me. Thank you.
Bye. Thank you.